Hi everyone, welcome back. It's time to start talking about Venus. In our last discussion, we got into the first planet in our solar system, away from the Sun, that being Mercury. And now we turn our attention to Venus, the hottest planet in the solar system. Here is a picture of Venus taken with the Hubble Space Telescope, and not all that many features, really, because we have these clouds which reflect a lot of the incoming sunlight. In fact, Venus is the most reflective of all of the planets. It has an albedo of about like 0.67. And one of our big questions is, why is Venus so darn hot? And also, why is it so reflective? So we'll get to that as well. And some others that we will concern ourselves with was, how is Venus formed? Why does it have almost no rotation? How were its volatiles lost? How did its atmosphere evolve? And what are some similarities and differences between Venus's climate and what will happen with Earth? So some quick facts about Venus. Venus is a little less massive than Earth. It's a little smaller. It has a little bit less density. But all three of those, mass, density, radius, they're very similar to those of Earth. Rotational period, however, 243 days. And it rotates in the wrong direction. In other words, the sun rises in the west and sets in the east. It has a very circular orbit, though. On average, Venus is about 0.7 AUs from the Sun. So remember, Mercury is 0.4, Venus 0.7, Earth 1. Mars is about 2, Jupiter 5, Saturn 10, Uranus 20, Neptune 30. Just getting a sense of the scale of the solar system. Now, Venus's axial tilt, you could either call it 2.2 degrees retrograde or 177.8 degrees prograde, but basically Venus is flipped upside down, so to speak, and its rotation has virtually been stopped. Satellites, it has almost no satellites. Other facts, so we already mentioned its albedo reflects about 2/3 of incoming sunlight. And surface gravity, it's a little less than that of Earth. Temperature, though, the hottest in the solar system. Surface temperature, 740 kelvins. The atmosphere is extremely dense, 96.5% carbon dioxide. That provides a huge greenhouse effect given the concentration of it in the atmosphere. Venus's atmosphere is about 92 times as dense as Earth's atmosphere. Now, there's also a small amount of sulfur dioxide in the atmosphere, and when you combine that with the very small amount of water vapor, that actually goes into creating sulfuric acid, which is why it has those clouds that it has. The clouds that you see are sulfuric acid droplets, which are very, very reflective. That rotational period of 243 days is believed to be due to the fact that early in its formation, Venus suffered one or more giant impacts. In fact, it may have originally had 2 moons due to these impacts, and these moons themselves, I mean, when you have 2 decent-sized moons around a planet the size of Venus, that's a gravitationally unstable situation, and the result will often be that one of them ends up getting ejected from the system while the other crashes into the planet. And that can further slow down the planet's rotation. But still, we're not quite sure exactly why Venus rotates so slowly. Interestingly, Venus has a little bit of a resonance with Earth. It revolves around our sun almost exactly 13 times for every 8 times that Earth orbits the sun. Now, that atmosphere, 96.5% carbon dioxide, and then that 3.5% molecular oxygen, and I already mentioned that sulfur dioxide, which combines with the water vapor to create sulfuric acid, which it actually rains sulfuric acid on Venus. The amount of sulfur dioxide in Venus's atmosphere changes very greatly with time, as we will soon see. But in any case, that can combine with the water vapor, create sulfuric acid, and it will rain sulfuric acid on Venus. However, that rain will actually not reach the surface, but it can collect on, say, a descending spacecraft, causing some metallic frost to condense, combined with other things in the atmosphere. And that's actually exactly what happened when the Venera probes entered Venus's atmosphere back in the 1970s and 1980s. They encountered a big power spike, and the realization was that metallic frost was condensing onto the probes. Surface winds on Venus are actually extremely calm, but upper-level winds are fairly decent. They encircle Venus about once every 4 days, and we call this, quote, super rotation, because these winds are going around much, much faster than the rotation speed on Venus. Now, there is, as we know, a runaway greenhouse effect on Venus. You probably know that carbon dioxide is a greenhouse gas, and on Venus it's a very powerful greenhouse gas. Interestingly, though, we believe that Venus was habitable potentially up until about 2 billion years ago. In fact, we think it probably had liquid water oceans on it until about 2 billion years ago. So it was habitable for quite a long time. But eventually, as our sun continued heating up, those oceans would evaporate. Water vapor, as you hopefully know by now, is a strong greenhouse gas. Whether it's on Earth, whether it's on Venus, water vapor is quite a strong greenhouse gas. In fact, when the oceans on Venus evaporated off, that raised Venus's surface temperature to 1800 kelvins, which was hot enough to melt rock. And I mean, 1800 kelvins, that's really hot. It's much hotter than Venus is even today. But eventually, as that rock melted, that released a lot of carbon dioxide into the atmosphere, increasing the temperature even more, I think up to over 2000 kelvins, until eventually the lighter water vapor molecules were eventually photodissociated by ultraviolet light from the sun, and the water vapor ended up eventually getting destroyed and escaping from Venus's atmosphere. So as a result, Venus's greenhouse effect today is primarily dominated by carbon dioxide. So with this in mind, this implies that Venus used to have a lot more water than it does now. So that leads to an experimentally testable hypothesis. If Venus had a lot more water than it does now, then that would mean that you would expect to have a higher ratio of deuterium to hydrogen than Earth has, because as the water vapor gets photodissociated by the ultraviolet light from the sun, the parts it's going to escape is going to be more likely the lighter ordinary hydrogen atoms, whereas the heavier deuterium atoms are more likely to stick around. And indeed, Venus's atmosphere has 120 times as much deuterium as Earth's atmosphere has. So this testable hypothesis from this whole theory of Venus's atmospheric history turns out to be in very nice accordance with observations. So anyway, as a result, Venus's atmosphere eventually cooled down to 740 kelvins, which is still hot enough to melt lead. So you definitely would not want to go there to visit, especially without a heat insulating spacesuit. Surface pressures there, as well as an air-conditioned spacesuit to get your body heat on. As we mentioned, surface pressures there are 90 Earth atmospheres. That's really why all of that carbon dioxide is able to produce such a powerful greenhouse effect even now, because there's just a whole lot more of it. Though when Venus was at its peak in terms of temperature, it actually had probably an atmospheric pressure of about 300 Earth atmospheres, because of all of the water vapor there. And again, water vapor is a very powerful greenhouse gas. So, in any case, Venus is now a hot, dead planet. Now, when I was your age, I thought it might be possible to terraform Venus by, when we say terraform, we mean changing a planet's environment into something that is more hospitable or more habitable, similar to, more like Earth. But maybe you could release lots of silver iodide crystals into Venus's clouds, causing them to rain themselves out, getting rid of the greenhouse effect, and could potentially cause the surface to cool. So what was wrong with my reasoning? So I'll give you a few seconds to pause the video and think about what was wrong with my reasoning when I was in high school. So, if you've thought about it, you recall that Venus's greenhouse effect is primarily caused by carbon dioxide, and that is not going to be affected by releasing silver iodide crystals into the clouds. So it's like, sure, you might get the sulfuric acid to completely rain itself out, and fine, you'll be able to see the Venusian surface. That won't get rid of the carbon dioxide. In terms of mountains, well, Venus, it turns out, is a lot flatter than Earth. You're going to see some cool pictures like this that's like, wow, this is a really cool terrain. Unfortunately, the vertical relief on this has been exaggerated by over a factor of 20 to bring out the features. In truth, this is much flatter than what you see. And that mountain that you see, Gula Mons, nice looking volcano, it would actually be pretty easy to hike up that. So Venus does nonetheless have some high mountains. Maxwell Montes is the highest mountain on Venus with a height of 11 kilometers. And then there's Mat Mons, which is shown in the picture here. It's a volcano. It's the highest volcano on Venus. That's about 8 kilometers in height. You might recall that Mount Everest is about 8,850 meters, so 8.85 kilometers. However, on Earth, the ocean trenches can get very, very deep. The deepest part of the Pacific Ocean, the Marianas Trench, Challenger Deep part, is over 35,000 feet deep below sea level. So compare the highest part above sea level. Well, technically that's Mount Chimborazo in Ecuador. When you compare like highest part above the surface of Earth, or the center of Earth, but in terms of average sea level given the shape of Earth, you're talking about Mount Everest, of course. So the difference between Mount Everest and Challenger Deep, we're talking about 64,000 feet difference. So that's on the order of 20 kilometers. So in any case, Venus's surface on average is several hundred million years older than Earth's surface. So apparently, even though Venus, we now realize, does have volcanoes, including active volcanoes, the rate of resurfacing is much slower than that on Earth. Well, that might not be surprising because Earth is mainly resurfaced not by volcanic activity, but by plate tectonics. So plate tectonics resurfaces Earth on average every few hundred million years, which, not surprisingly, is the supercontinent timescale on Earth. So on average, every few hundred million years, you go from a big supercontinent to a few different continents spread out around the planet, back to a supercontinent 300 million years later, on average. Also, nonetheless, though, Venus is volcanically active, and it's the volcanism that injects sulfur dioxide into the atmosphere, which, combining with water vapor, can help you to create the sulfuric acid. Venus has a sulfur cycle. Just as Earth has a carbon cycle, Venus has a sulfur cycle. There's also a nice diversity of volcanic features on Venus. Things like pancake domes, arachnoid domes, and coronae are examples of such features that are not found anywhere on Earth. So these pancake domes are much bigger than lava dome volcanoes on Earth. They are very flat, as their name suggests. They're not found anywhere else in the solar system. And here's a picture of these things. Then there are these things that are called arachnoids. Their origin is unknown. They're not found anywhere else in the solar system as well. They have these kind of weird, funny features, as you can see. And then you have these coronae. They're not found on Earth, but they actually are found on Uranus's moon Miranda, which we'll discuss in more detail when we talk about Uranus. Uranus is a very special planet in terms of one of its moons in particular, Miranda. So here are these coronae. Now, in terms of the geology, again, Venus does not have active plate tectonics. Earth is the only official planet in the solar system that has active plate tectonics. In fact, Earth is one of only 3 bodies in the solar system that we know of to have active plate tectonics. The other 2 are Jupiter's moon Europa and the dwarf planet Pluto. But nonetheless, between 400 million and 700 million years ago, Venus did have a major resurfacing event that effectively resurfaced the entire planet at once. Apparently a big situation where the entire crust collapsed into the mantle, fresh lava overflowed, created new crust. Fortunately, stuff like that does not happen on Earth. Active plate tectonics helps to make things like this happen more slowly and gradually. So if that did happen on Earth, that would be pretty bad for life as we know it. Venus also has river deltas, but these were not carved by water, they were carved by lava. One of them, Baltus Vallis, is about 4,200 miles long, which is longer than the Nile River. So you could call it the longest known flow region in the solar system, although in fact it's a bit longer than both the Nile and the Amazon being the longest river on Earth and the largest. So here is Baltus Vallis, which was carved out by lava flows. Some cool-looking volcano features, like Gula Mons. I showed that off in the distance on a previous picture. Again, the vertical relief on this is exaggerated by over a factor of 20, so it's really not this high. But to bring out the features, they did that, and that makes it look nice and cool. In terms of craters, Venus has almost no small craters. It basically has no craters that are smaller than about 5 kilometers. I'll give you a moment to think about why. Why would Venus not have any craters smaller than about 5 kilometers in diameter? So, the answer, if you need to pause the video, you can do so, But the answer, why Venus doesn't have any craters smaller than about 5 kilometers in diameter, is because Venus's atmosphere is so thick. So the smaller bolides that would create the smaller impact craters are burnt up in the atmosphere. So the ones that make it through are the really large ones, and they create big impact craters. Now, in terms of exploration of Venus, back in the days of the kind of, I guess you could call it the peak of science fiction, which kind of gave birth to a lot of the science fiction that we have now. Back in the 1940s and 1950s, a lot of authors thought about the possibility that maybe Venus is this nice steamy jungle that could have all sorts of life thriving on its surface. Unfortunately, these hopes were dashed when in 1962, the American spacecraft Mariner 2 reached Venus and revealed that even though the white cloud tops are cool, the surface is very, very hot. In fact, we'd even had hints of this back in the 1950s because of radio telescopes. In any case, in 1966, the Soviet Venera spacecraft, Venera 3, crash-landed on the surface, becoming the first man-made object ever to reach the surface of another planet. And then Venera 9 in 1975 was the first spacecraft ever to transmit surface images of another planet. And then in 1982, the Soviet Venera 13 became the first and still only spacecraft to transmit color images from the surface of Venus. Now, this overlooks the fact that a whole lot of missions that they launched failed. In fact, pretty much all of their missions to Mars failed, whereas the United States succeeded in a lot of those, starting especially in the late 1960s and mid-1970s with missions to Mars. Interestingly, since 1985, no spacecraft has visited Venus's surface from any country. Here's a picture taken by Venera 13 in the early 1980s when it reached the surface of Venus, a color picture of the surface of Venus. It wasn't a rover, and it couldn't really orient its camera very effectively, but nonetheless we see the picture of the surrounding land, the sky, and the spacecraft itself. Now, you might wonder, shouldn't the surface be dark with all of that atmosphere? We can't see the surface. Well, remember, even though 2/3 of incoming sunlight is reflected, 1/3 of it does get scattered toward the surface. And remember, Venus is also closer to the sun, so the planet itself would see the sun being about 50% brighter overall than if you were on Earth. So 50% brighter and 1/3 of the sunlight reaching the surface. So you're talking about, effectively, you would expect the surface to be about half as bright as the surface of Earth. So yeah, and since you're dealing with so much in the way of clouds, the light gets scattered all around. So instead you get this kind of goldish sky. More recent missions. The Magellan Spacecraft was an orbiter in the late 1980s and early 1990s that basically mapped the entire surface. And it was really from the surface mapping that we got those pictures of Guillemons and Matmons and such that I showed you. They were recreated, they were re-rendered based on the data from Magellan, and then artificially colored in to depict what we think it would actually look like. Now, in terms of future missions to Venus, the European Space Agency launched the Bepi-Colombo mission, which will actually go into, I guess, orbit around Mercury in 2025, but it did fly by Venus in 2019. And also, the Venus Express spacecraft was able to give us some more knowledge on Venus, including knowledge about its active lava flows and stuff like that, its active volcanism. And that was intentionally crashed into the surface in 2015. But the Japanese Akatsuki spacecraft went into orbit in Venus in 2015. One of its goals is to confirm the presence of lightning, confirm active volcanism, and it has a number of other planned experiments as well. Amusingly, its initial orbital insertion failed in the early 20-teens when the retrothrusters misfired and the spacecraft just sailed right by Venus. So it took it a while to kind of lap Venus again to catch up to it, and once that happened, the retrothrusters were fired again and orbital insertion worked. So here's a picture taken in ultraviolet light of Venus from Akatsuki. Here it is in infrared, very cool. And combination of daytime and nighttime side in infrared. Some early results. Well, lightning has been confirmed in Venus's atmosphere. In particular, they measured electric fields, which would cause dielectric breakdown. And when that happens in an atmosphere, we call that lightning. What about humans on Venus? At first, you might think, it's like, well, are you insane? I mean, Venus has terrible conditions. Well, actually, Venus contains conditions most like Earth anywhere in the solar system. Well, wait a second. What about being hot enough to melt lead and atmospheric pressure 92 Earth atmospheres and stuff like that? Turns out that once you get high enough in the clouds, the temperature can be quite nice. You wouldn't want to breathe the air, though, so obviously you would need to bring oxygen with you and stuff like that. But you could potentially deploy balloon missions and stuff like that. So maybe some nice science fiction novels based on these types of ideas. So in any case, that is the end of our discussion of Venus, and hopefully you have some more insight into the hottest planet in the solar system. Next, we will turn our attention to Mars. That'll be the next video, and I'll see you then. Thank you for watching.